of I'd like to present the results of our work, which is semester thesis on aerial navigation correction via arbitrary visual feature matching. I'd like to thank to Igor Krasheny and Alexander Marchenko, who've been advising me throughout this work. And let's talk about the plan. So the plan for today is cover several topics. First is the motivation research goal. Then I'll cover the outcomes of related work analysis and come to research gaps and objectives. Then we'll talk about approach to solution, data sets that we used in this work, evaluation, and finally the results. Also, I'll mention the limitations and the comments from the reviewer of the thesis. Let's start with the motivation. Motivation is pretty obvious because what we have when it comes to drones flying and relying on GPS signal is that sometimes they lose the signal due to different things. Well, in the case of warfare, it's even more obvious. So there is a jamming and well, let's say jamming, that's enough. And it makes aerial navigation challenging because inertial methods, they work, they are kind of robust, but they accumulate an error over the time. And we have a kind of, well, I have to say a word that this thesis came from real problem with specific UAVs, which are using particular methods, which are a superpoint plus superglue running on Raspberry Pi, and kind of everything is good, but they fail on certain cases, and these cases are rural areas with like non-obvious landmarks, and this is what we wanted to try to improve. So the initial need for the research was to find a better vision model for navigation correction task. As I said, we wanted to find a substitution plus for superpoint plus superglue, which will have no issue with no corners like landscape, let's say, and will have a comparable performance. To say about the contributions of this work is that we are doing baseline evaluation of superpoint plus superglue versus eLofter and enhanced version of it, and we do experimental validation of the proposed approach. Starting with the related work, there are a number of papers published on computer vision problems and kind of related to our problem. First one is Match Anything. This is really profound work which is focused on training and evaluation of cross-modality measure, but universally. Universally, they don't focus on UAV task and they don't focus on aerial navigation. They just try to find something that will perform in all the cases like kind of best. And they find that find Roma model is kind of wins for all the cases, but it's not suitable for us because it's heavy and they don't have hardware limitations. eLofter is a runner-up. This point is kind of one of the bricks that made a choice of eLofter for our work. Another paper is Mismatched. They do very comprehensive comparison in different scenarios, like including aerial navigation, but they lack of real aerial data to cover the case again. And their conclusion is that method choice is context dependent. Then we explore the available methods, and I'd like to elaborate on that a bit. For feature matching, there are different approaches. It all started with traditional methods, which are very efficient, and in many cases they perform really good. But when it comes to low textured region or repeated patterns, they fail, and they are not learning based, so we cannot improve them with the data. With the data we possess, we can. There is another group of methods which are learning based, and here we have our superpoint, which actually which has some very straightforward benefit, that it has no need on data labeling. It is trained on self-supervised approach, and this is kind of this is really important because we have problems with labeling with the data. I'll cover that a bit later, but when it comes to data, there are really strong issues that remains unresolved. But it's based on corner detection, and this is how we came to this thesis. Detector-free methods is a sort, let's say maybe sort next evolutional step of detection models. They don't need key points like superpoint, and they use usually they are based on transformer architecture, and there is a group of methods like elofter and Roma mentioned already that may be suitable for our task. And their advantage is that there is no this key point detection, which we had in superpoint with its corner case. So when it comes to lofter and elofter, local feature transformer and enhanced local feature transformer, they are built on several layers of work. First stages. First of all, they do feature extraction, then coarse level matching, and fine level matching is performed. And here on the image we have comparison, not an real data, but this is a reference image from the paper. That elofter is strongly outperforming super glue with superpoint on reference scene. Now we came to research gaps. One of very important research gaps in all the area is the lack of benchmarks for negative pair evaluation. For our case, we want to actually we want to do binary classification and find a tile of map which is which represents our current location. This is why we want to have a robust binary classifier out of matching pipeline, and all the works that I mentioned before, they don't do negative pair evaluation at all. Another thing that all the aerial researchers, they are focusing on urban scenes. And urban scenes, they're kind of rectangulars and lines. And when we work in rural areas, then we come to the issue that it's not properly covered in researches. So the idea was, and then we came to idea. Well, there is some jump, but well. Yeah, I had to think. Yeah, I had to say a word about this. When we talk about transformer-based architectures, they are heavier. They're significantly heavier than traditional methods or superpoint and superglue, which are which actually run without need of GPU. And we had to think about whether we can do something comparable in performance. And when we talk about eLofter, it was enhanced version of Lofter, which was a speed up, 2.5 times speed up over the initial models. But in the related work, it was still 2 times slower compared to Superpoint plus superglue. And this is how we came to this idea to try to implement early stopping based on matchability in eLofter. And then, of course, design and evaluate benchmarks, including negative error tests. This idea elaborated. We want to try to do a thresholding on confidence scores, which is an idea stolen from late glue, evolvement of super glue implementation. Try to do this early stopping in transformer model on some threshold values. And this is our idea. Another thing that actually was required to do anything to start with this work is to prepare the data for baseline evaluation. And we had 3 data sets for that. First one is UAV log, is a public data set. Well, I'll elaborate on that. AirSim and our proprietary data. Then we implemented evaluation framework and run baseline experiments comparing Superpoint plus superglue with eLofter. And again, M for eLofter improvements is scoring and early stopping and evaluation. So the data sets. The first data set is UAV log. It's a public data set, one of the best data sets available for aerial imagery, which contains kind of 7,000 drone images with attached 11 satellite maps captured in China. But there is a problem with it that actually, well, there is a really big problem with that data set, because actually some of those images were, first of all, we didn't have correct camera intrinsics. It's just something declared in the dataset definition description, but in fact that was not true almost for every flight. And even if well, I would say that out of 11 scenes, because each satellite map corresponds to some flight in different region, I think that 7 were more or less precise, but nevertheless, they were not perfectly aligned, and kind of making pairs out of these aerial images and satellite data, satellite maps, was kind of a challenge. So yeah, we had to filter that data. Then we had a really sweet data set generated from Microsoft open source simulator, and it's I would say that it's a magic, because it's really close to what kind of real images, real photos, aerial photos resemble. But we have a perfect alignment, pixel perfect alignment, and we can do anything we want. We can generate different weather, different seasons, and so on. Yeah, but it's still synthetic. And then we had our proprietary data set, which was kind of made in Ukraine. But it's kind of it's a bit small. We had like 700 pairs, and we didn't have camera intrinsics here as well. For the evaluation, we use the next metrics. We use for quality, we use mean corner error. inlier ratio, area under the curve for the classification task, and for performance metrics we use matching time. For the pose estimation, we use Ransack built-in from OpenCV with the following parameters. Early stopping. Since efficient Lofter executes fixed number of self-cross-attention blocks for every image pair on coarse level, then we assume that it is not required to pass the full length. And by attaching confident heads to every block, we can try to do early stopping and evaluate whether it still resembles the confidence level, appropriate confidence level. Again, I'm talking about coarse level coarse level only. So this is the diagram of the Elofter architecture with the early exit condition for early exiting to the fine matching block. Here I show the well, this slide is about thresholding. This thresholding kind of out of the air, but this table shows actually the results of grid search for reprojection error when we were evaluating the methods, and it could be interesting to point on that configurations that we tested over the baseline evaluation. And here we have, I'll stop on that a bit more, but we have superpoint plus superglue with different number of max key points, and Elofter, base Elofter, and Elofter with confidence score with 3 levels of confidence scores, which we actually take from light glue paper and do the same. And here the table of evaluation summary on the first data set, on Vislog data set. What we see here is that actually I would be pointing on AUC score only. When we talk about AUC for Elofter with confidence, with reduced confidence, we see that it changes really insignificantly when we get to minus 10%. Then we have some drop in score, like one hundredths, and some performance improvement, 3 milliseconds. So it takes 3 milliseconds less. And what we see also that when we use superpoint plus superglue with its like base configuration for 1,000 points, which is quite a lot for superpoint plus superglue, we have it faster, 1.5 times faster on our test configuration. But when we set amount of points, something that will be close to dense matching, we see that Elofter actually outperforms superpoint plus superglue twice. When we go to AirSim, this is our data set with perfect pixel alignment. We see different results. Elofter is finding a lot of matches, really many matches, because everything is so similar to it. There is no uncertainty, and we have 3 times lower inference times because there are too many matches, and it takes time to pass over the fine levels. And when we get to our real data, we see something close to UIV Vislog. Here are the some charts. I think it's better to look at them will be from monitor, but what is interesting here maybe is a number of matches, which is we see that for the top line is positive pairs and the bottom line is negative pairs. We see that for superpoint plus super glue, the number of matches is always pretty low. It's somewhere around 10 matches for the image pair. But when we get to Elofter, to dense matching method, we see that for positive pairs, the count of matches is somewhere over 100. But for the negative pairs, we see a really low amount of matches. Yeah, and for the curves, for this log data set, we see that binary classification is almost useless for superpoint plus superglue, but when we use Elofter, it's I provide here reference for one confidence level, 98, and we see that it's kind of really good, 92%. Here are some reference images. That we see that superpoint plus superglue, we see that there are some matches. This is, let's say, this is urban area. But when we get to dense matching of Elofter, we see really a lot of matches. It's 400 matches for this image, for this pair. And when we get to some more challenging case, superpoint plus superglue is getting lost. But for the Elofter, there are still decent amount of matches, which would say that making it robust in this scenario. Yeah, I think I would not stop on AirSim, but show the images. Here we have the score, classification score, even better. But yeah, superpoint plus superglue again. Well, not good in challenging scenario. For the same challenging scenario, the different seasons, we still see that Elofter is performing quite reliable. And our custom data set still good for the Elofter, not bad for superpoint plus superglue, which actually makes this method usable in real conditions. But challenging pair shows that there is some mess with superpoint plus superglue in this case. For the same pair, Elofter performs pretty well. And here even more challenging. There are no let's say significant features on the image found on this image is found, but again Elofter finds them pretty well. Again, I'm talking about the base version of Elofter trained by the authors of the model. Yeah, so the concluding remarks that we conducted research on a baseline, and I was not stopping pretty much on this. It's in the thesis, but not in the slides. We see that, yeah, we see that scores on data sets. Classification scores are pretty similar, and corner error or count of matches, they decrease gradually when we reduce the confidence threshold. So this makes actually makes space for the using of improved model with a reduced inference time. And to maybe, yeah. Well, let's say a word on limitations in future work. No, I'll elaborate on thesis review. So I've got a number of remarks on my thesis. And I would like to highlight some of them, but maybe we can leave it for the question and answers. I would say the limitations. Limitations is that we use mean corner error as a metric for our calculation, which is kind of maybe unfair for the real conditions. And this is point in the review. For the data sets related, I didn't do separate cross-model evaluations for different seasons, and I didn't do fine-tuning of Elofter on season aerial data. I can elaborate on that further. And the things actually very wide. The area for further exploration is very wide. First of all, we can investigate early stopping in fine matching layer, yeah, right, because we have two layers, coarse and fine. We can try to do even more performance improvement. There is another point that is pointed by original author, that global context in Elofter architecture may also contribute to some accuracy. And also we wanted to explore the alternative approaches, which is using of segmentation models like SAMSIM or Mask2Former, which is kind of really alternative approach. So I think many thanks for your time, and I'll be glad to answer your questions.
Thank you very much for your speech. Very interesting and very important solution, especially in our conditions. So my question is, do you have any prototype of your solution? And if yes, which TRL level you have?
If yes, what? Sorry?
Prototype and TRL level.
Okay, technology readiness. Sorry for this question. Yes, we have the prototype, and it's a bit maybe I would say maybe it's not ready for production. So there are a lot of I would say that challenge with the data is not fully addressed yet, because we have this misalignment and. Yeah, so the main problem that I currently have is having more data, more accurate data for testing.
Thank you. So in our conditions, very important to have autonomy devices like this, that is for copter type or for plane. So for solving task, recognition different type of object on the battlefield, tracking this object, and finally hitting, we need to have technology like this. So, but exist alternative method, video flow, you know, maybe that's a different type of sensor implemented on board. There is gyroscope and LiDAR and a lot of different type. And information from this sensor computing on the CPU, which located in this port, and which systematic error has your approach, for example, for deep strike or for middle strike distance?
I would say that our focus on, if I correctly understand, on deep strike, right? Because we are not limited with the distance, and we are investigating this solution for high altitude drones flying deep and far. But I think I struggle to compare the different methods. They all good in certain cases, but they have their limitations. So, yeah.
Flying in jamming condition without any GNSS signals, that is very important. Thank you. Maybe this solution we need to close, because it is not in open access, must be both, because
Yes.
Katsap's
Thank you very much for your research. I have one question. What is the target device of your solution is drone?
Yes.
What is the size of your model? It's transformer based.
Yes.
What is the size?
Did
you try to deploy this model on real device, or did you use some kind of knowledge distillation, quantization, whatever?
It is definitely, there is a definite need for quantization and reduce of the model for actual deployment, because the drones that are currently in production, they don't have any GPU on board. And for transformer, we need GPU. So it was kind of, it was a part of research to find out whether it is feasible. So find a feasibility, define a feasibility of this solution for equipping the drone with Jetson, with NVIDIA Jetson. And on Jetson, we can run distilled and reduced model.
Thank you. And one more question, please. Your approach based on so-called early stopping.
Yes.
What happens if your model stops mistakenly too early? You just rerun, or it happens something not good?
I think that we will have bad classification. So
is it problem or not? I think if in real life you have a video stream and you don't need to analyze each image, just in so you just rerun, right?
Yes, we rerun, and we are talking about navigation correction. So we still have inertial navigation module, and our concern is an error that accumulates with this inertial system.
Thank you. Thank you.
Okay, I have a couple of questions. My first question about the novelty in this work. Could you please summarize very briefly what is novel in this work?
Novelty.
I mean, scientifically novel.
Sure. So the first thing is that the early stopping, which makes improvement over the original method. This idea is taken from another model described, as I mentioned, from light blue. Second is the lack of, first of all, of specific aerial navigation baseline comparisons for those methods that were included in this review. And second is absence of classification, evaluation of binary classification, which we do here.
I'm sorry, I doubt that early stopping is a fully novel thing, and you confirm this by pointing to some other model which was the prototype of that. Is the early stopping you include in your model really new, a new approach?
This is a new approach for this particular model, and for transformer-based.
So it's novel for transformers.
Yes, for eLofter.
Okay. My second question is about your rebuttal. Did your reviewer saw your rebuttal?
Sorry.
You wrote some answers
yes.
to the criticisms
yes.
by your reviewer.
Yes.
Did he see your answers?
You mean those?
I was looking at the documents that were provided together with your dissertation. I saw the review, which has been written in English.
Yes.
I saw your answers to this review, which were written in Ukrainian. Can we expect that Camille understands Ukrainian better than English?
Okay, I think that you're referring to the. We had two passes of review. There was preliminary review, which I've got in kind of informal way. And I didn't treat it as a formal document that I have to answer in a formal way.
Yes, that's correct.
Okay. Okay, thank you.
I have a very short question. First of all, thank you for the presentation, but the title of your thesis is Aerial Navigation Correction.
Yes.
But you were talking about feature detection, not...
Well, yeah, there could be some misunderstanding. We are really working on correction task, as I mentioned, because we are trying to reduce this inertial navigation error with our pipeline that we introduce here.
Did you then verify how your new method improves aerial navigation?
It was not tested in real condition yet because, as I said, there is no hardware ready to deploy on. So it will be, I hope, tested, and then we will say that yes, how properly this problem was resolved. So maybe I had to name the work like a way to aerial navigation correction.
Yeah.
Thank you. I want to get back to the review. And Dmitro Mishkin mentioned this major issue with AUC approach.
Yes.
And he claims that you cannot use AUC in the setup of this paper. And I don't want to read the whole part.
Yeah.
But I do not see your objection on this.
Well, I think I wanted to address it here on this point that should be based on model output without Oracle knowledge. Actually, yes, there are two parts. You're right. First of all, it was not properly mentioned in the work, and it's a flaw, I admit it, that actually the scores, the AUC metric was calculated without Oracle knowledge. It's not implicitly stated, but it was done this way. Second thing is, yes, actually it is. It can be addressed probably or explained, or I don't know, just like try to explain why I used MCE score, because I had this misalignment on all the data sets besides the AirSim. This is why, and every data set has different deviation, different mismatch, pixel level mismatch. Only on AirSim we had this pixel perfect alignment. So I used MCE, and in real world condition, as a reviewer properly stated, it is kind of trick to use it this way. So the idea how to address it, the proper idea how to address it is to have camera intrinsics. Because since I didn't have it on my data, I had to kind of do this synthetic comparison on every data set. In real world conditions, we need the intrinsics, and then we can use L2 score or set a threshold, actually define a threshold.
And when you mentioned camera intrinsic, you mean?
I mean that we don't know the we don't know the actual angle of the camera when the drone flies. We don't know the actually focal lengths of the camera. We had to estimate it, but it was not something that was given in the data.
Yeah, but okay. So let's imagine and get back what Sergei mentioned about real life implementation.
Yes.
So is this intrinsic data available if you're talking about UAV?
It is available, but for the scope of this work, I didn't have it.
Yes, I understand. But in terms, if you want to implement your method on a drone.
Yes.
So this data is available and we can integrate it into the model.
Yes. Yes, and then we can change the metric. Well, actually, we'll still be calculating AUC, but we'll be not using MCE. We can use inlier ratio or L2 distance.
Okay, thank you.
Okay. We have one hand raised from online audience. Ola? Can you maybe tell it louder and
okay, so first of all, thank you for the presentation. Could you scroll back to the slide where you compared eLofter to SPSG on the Wislog dataset with a table?
On which?
Wislog and SPSG in a table.
Mm-hmm. Yeah.
Yeah. So basically,
yeah,
that's the one. Based on the results in the table, SBSG completely fails on that task. AC of 0.5 means that it basically guesses randomly. So why did you decide to compare this method with eLofter and not something like more suitable?
Because we had 3 data sets, and for the data set we are most interested in, we actually, here. Sorry, I think. So with the Elaine data, we had some performance on SuperPoint plus SuperGlue. This is the first reason, but maybe the second actually, because the first reason is that we had some real working model in real conditions, and we wanted to compare this model with something that could be better.
Okay. And my second question is, could you scroll back to the previous slide?
Yeah.
How does it happen that SPSG starts performing worse when the resolution of the image increases? So here, for instance, SPSG on 512 points, it's worse than the one on 1496.
I think that it comes out of like more noise that is generated by more points. Here I just show the result that the evaluation results, which were I would say that not deeply investigated why it happens in this case, why performance becomes worse. I just took it for granted.
Okay, thank you.
Thank you, Ola.
We have another question.
Yes, but we are running out of time, so maybe one quick question and
so you have developed an image matching algorithm. How does image matching translate to actual localization of this drone?
As I said, we have, well, if we talk about binary classification, then we have a drone with the maps on board, map tiles, and we try to find out the correct tile of which represents the current location of the drone.
Okay, thanks.
Thank you.
Another question regarding this metric table.
Mm-hmm.
Do you measure this latency see inference time on a deployed prototype, or it's like local experiment with GPU?
It's a local testing, as mentioned in the thesis. Yeah, maybe it's not available for all the, but yeah, okay, it's available. We were testing in local conditions.
Okay, so it's not like
it's not just on board. So yeah,
okay,
it's local conditions.
Yeah, thank you.
Thank you, Ola.
Thank you.
Okay, so let's move on to the next presentation by Bogdan Romanchuk. And he was also advised by Igor Krasheny, and he will be presenting work entitled Edge-Friendly Multiple Instance Learning for Region of Interest Proposal.
Hello to everyone. So today I will present you with our study called Edge-Friendly Multiple Instance Learning for Region of Interest Proposal. My name is Bogdan Романчук. My advisor is Igor Krasheny. So here's the agenda of my speech. First, I will provide you with motivation, problem statement, and introduction. Then I will review some related work. Then I will propose you the approach, outline the evaluation pipeline, and highlight the results. So the Russian Recon Strike circuit, which consists of Scout UAV, typically Orlan, and ballistic missile launcher Iskander, has become a major threat to Ukrainian forces, and its most impact is that it shortens the time from detecting the target and hitting the target. And the obvious way to deal with this threat is to detect and strike the recon drones, but traditional air defense rockets are costly. And so the kamikaze UAVs have become a low-cost anti-aircraft system. And so the first task that naturally arises in the computer vision setup is to detect a small region with distant object. In this case, it's Scout UAV in a high-resolution frame. In this particular frame, the target is occupying only a dozen of pixels, and